never stop learning because life never stop teaching. A very pleasant good morning to one and all present here. I welcome you all to CIT Quantum Hackathon 2022 workshop series sponsored by IBM Quantum as a part of Qiskit Focus. First of all, congratulations to all the participants for stepping forward. So it's my privilege to welcome our honorable chief guest and speaker, Ms. Soyoung Shin. She majored in both electrical engineering and physics and worked as a space vehicle system engineer. Sophy is leading the quantum and the Qiskit community in Korea to build an inclusive and sustainable quantum community in Korea. Sophie is interested in adopting Qiskit into different types of quantum hardware and also interested in achieving better performance from the quantum devices by low-level control of qubits. Ma'am, once again, I welcome and extend my sincere gratitude to you for taking your time to share your quantum knowledge and experience. We are so thrilled to listen to you on the topic Qiskit Pulse tutorial. The session is all yours.
Yep, thank you very much. And I will start
Yeah.
share my screen. Okay, so everybody can see my screen now.
Yes, ma'am. I can see.
Yeah, thank you. Thank you for introducing me, Rishma. And hello, my name is Sophie, and I'm a Korean lead surviving quantum in Korea. And I am a Qiskit advocate since 2020 and currently leading whole quantum and Qiskit community in Korea. And I'm a founder of a Qiskit Korean community. And also, I would like to deliver my special thanks to Professor Manjula that Manjula professor will sincerely support our Qiskit community activity includes hackathon and our international symposium satellite event by attending as a mentor and also giving a special talk there. So today I want to introduce you about the Qiskit Pulse, a kind of a powerful weapon for quantum kernel developers, which working between the hardware devices and the quantum algorithms. So let me start first introducing the near-term devices. So as you know, we are living in the NISQ era, like our quantum device is not that perfect. And also it has a lot of noise and a lot of limitation to working as a perfect and noiseless quantum hardware. So in hardware side, we have a challenge in system side and device design side to make a better performing hardware. And also we have a challenging in device verification to make a perfect chips. And also we are in facing a challenge to controlling the hardware devices. And before go further, let us take a looking in at the inside of IBM quantum devices. So everything for us starts at the laptop side. So we can compose a quantum circuit at our laptop. And if we try to build our quantum circuit, then it will go through the quantum hardware, means the devices by using the by using the cloud API. So inside of this system one of IBM, there is a control electronics. So it is very similar to how a classical computer use bits and quantum computer use qubits. And also our quantum computer have translated into microwave pulses to control qubits. And this is the backside of our system one. And the pulse travels over cables through a special refrigerator called a cryostat, transitioning from room temperature to minus 459 Fahrenheit. The extreme cold temperature enables operation to be performed on a qubit while avoiding noise that would affect performance. So we usually call it as a chandelier. So by controlling the qubit, you can explore a computational space that grows exponentially. Harnessing the computation space is what underlies the capability of quantum computing. So yeah, here comes the quantum processor. So if we compose a quantum circuit, it produces a microwave at the device side, and the pulse reaches the processor built from quantum superconducting circuit that form the qubit, the physical embodiment of quantum information. So If there is the measurement finished in the hardware side, then the micropulse interact with the qubits. They return the electronics where they are converted into classical bits to be interpreted by the user via the IBM quantum experience. And the signal all travels again to our desktop by using our cloud API, so we can get the result. So yeah, so we just took take a look around what happens inside of our system, and we kernel engineers working between the software and hardware, and also the challenge for a software engineer, quantum software engineer, is a sophisticated compilation technique for the front end, like a gate-based, also includes some algorithms, and also the back end, like a pulse-based side. So the kernel engineer lives in here, the software side and both between software and backend. And Qiskit Pulse is an open source Pulse level quantum programming kit and first released to public by this paper at 2020. And the main motivation of Qiskit Pulse is provide hardware level access to the user mainly for optimal control of the quantum hardware and also for error mitigation and for dynamic decoupling. So again, go through what happens when you compose a quantum circuit is that when you first compose a quantum circuit by using quantum circuit libraries of Qiskit, it transposes interfaces gate according to its backend and define the register to perform the measurement. And the Qiskit send this information, the circuit and the register information to the quantum backend through its cloud API. Then it composes the actual pulse signal series to work with the superconducting qubit and the actual experiment open the quantum hardware. So after getting the measurement result by reading the classical register, the Qiskit API deliver this result to us. And to use Qiskit Pulse library, we need to take a look at some ingredient of a Qiskit Pulse. So there are several ingredients we need to take a look at. And first thing is the instruction. And the instruction to tell the hardware to do actual pulse operation. And there are four major instructions in Qiskit Pulse to compose a pulse schedule. Play, kind of play some signal on the pulse channel, and delay means that they will ask the hardware delay or wait some time before accepting some pulse. And shift phase and shift frequencies kind of increase the phase of a channel or set the frequency of the channel, usually blocked in using inside of pulse builder for the stable operation. So if you want to change drive frequency of a qubit, you need to set a outside the loop for this, and you will learn how to do this. Oh, sorry, this is a typo. And there is an instruction name as acquire, and this triggers the acquire channel to collect data for the given duration and store the measurement result in the registers. And this is the summary of all channels and pulse instructions of our first publicly released paper, and hope you take a look at this later if you are very interested in Qiskit Pulse. And before go further, I want to say that this will be uploaded at my GitHub as a public repo, and I already shared my GitHub repo with an organizer. So I'm sure you will receive that repo link soon as possible. So, and the aim of this Qiskit Pulse tutorial is give you a very good explanation and examples on how to use it. And before learning how to build a pulse signal for quantum backend by using our public account without premium access, let's simply check the circuit pulse experiment pipeline by using Qiskit. Just glance at the example of the typical quantum circuit, the entanglement circuit. And for this tutorial, I will use a pulse simulator and especially the fake backend to avoid a long queuing wait time. So before go further, let's start implementing some libraries and declare some simulator and backend by running this. So yet here I will use fake Valencia. Unfortunately, real Valencia is not available, but fake Valencia is one of the best fake backend showing very stable performance in everywhere. So at here, I'm using this. And connectivity of a fake Valencia is like this. And its max shot is 8,000. And you can check some specification and characteristic of a fake backend by typing this command. And before running this one, you need to import this. And we check the backend configuration now. And as I told you, every quantum backend have a predefined pulse sequence and schedules according to the quantum gate. So at here, let's check the Hadamard gate, the pulse sequence and pulse schedule of a Hadamard gate of fake Valencia. We compose this simple quantum circuit, and after transpiling the circuit according to backend, we can make and build and bringing the pulse schedule of this circuit by using this schedule function. So in these cases, the fake Valencia's predefined pulse schedule of a Hadamard gate looks like this. So if we want to check the actual pulse syntax and comment, we can just type this kind of a comment to filter. But yeah, the filter is just acting on some extrapolating the drive channel zeros signal into here. So you can see some shift phase and play drag pulse. Drag pulse is a simple Gaussian pulse, but have a second differential order of a phase signal into there to reduce some noise. And after that, you can also see the shift phase, and it looks like this. So let's check the X gate predefined pulse here. And the comment is like this. And here I would like to check the predefined pulse schedule of RX gate. And it is a little bit different. And you might notice or not, but the duration of a pulse schedule is doubled when you try to make a general rotation X gate. And as you can see, there is a two drag pulse declaration in this predefined RX gate pulse. And next target is our entanglement gate, one of the art of Qiskit pulse. And as you know, superconducting qubits using a cross resonance type of entanglement gate to make an entanglement gate. So as you can see there, we just use the qubit 0 and 1, but you can see there is a U0, it's kind of a control channel for drive 1. This is a drive channel for qubit 0, and this is a drive channel for qubit 1. It's a control channel of a qubit 0, and there is a extra pulse produced by the drive channel, a control channel to make a cross resonance to the qubit 1. And as you can notice, the duration of this entangled gate pulse is almost 10 times of a normal gate. So it is very easy to guess that if we just assume that our one qubit single gate have an error of 0.1%, then we can easily guess that it have around 1% of error because of the long duration of a pulse sequence. So that's why we need to reduce the CX gate and entanglement gate inside of our quantum algorithm, because it will produce a lot of noise and errors. And yeah, again, try to check the schedules. So, and if you're interested in explore more about the cross resonance gate, please take a look at this YouTube lecture by Nick Braun, because Nick is running a very interesting, this is a seminars run by Nick Braun, and this is very fine and very good explanation on the two qubit controls. And also Nick is running a Nick knows Qiskit YouTube series. So there you can find another very good lecture by Nick Brown through the Nick Knows series. So, and after that, after introducing our entanglement gate, I want to show you that not only the quantum gate has its predefined pulse sequence, but also the measurement itself is also a pulse operation. So we can just simply make a quantum circuit only have a measurement comment, and also we can check the pulse sequence of the measurement like this. And as you can see, the duration of a measurement is really long to get the whole information from the superconducting qubit. And as like that, it is just using a Gaussian square, like a simple square pulse to gather some information. And after getting information, it will record the result in the classical bit. And by summarizing everything, just build a simple entanglement gate. And this is a pulse sequence of a whole this simple quantum circuit. And as you can see, this is a Hardeman, and this is an X gate, and this is a cross resonance, and this is a measurement. So if we compose a quantum circuit at our Qiskit and in our clouds and laptop, it will produce this kind of a micro pulse sequence, and this sequence will be sent to hardware, and it will play. It must be played onto the superconducting qubit itself. So if there is someone who want to looking into the superconducting qubit itself or some dynamics of qubit in details, I would like to ask you to take a look at these materials to get more further knowledges. And I would like to skip to explaining everything in here because this is a kind of an introductory tutorial for the beginners, and also I aim to bring in interest from many of you to become kernel developers like me. So, as I previously explained, one of the aim of a Qiskit Pulse is optimize the hardware and getting a best performance. So at here, I will show you a very interesting tutorial to calibrate the X gate by using a custom pulse gate. So for that, let's make a simple X-gate circuit. And to get the ideal result, let's run the circuit at the simulator. And also we will run the circuit at our fake backend by using this command. And this is like that. So even though the predefined pulse gate is calibrated before running, its performance is not that perfect because the hardware always facing a very environmental problems and electrical problems. So even though we are really IBM Quantum really try to keep the hardware in the best condition, there will be always some errors and error to mitigate and noise. So this is the result. So the X gate needs to turn 100% for one result, but the fake backend result is not that ideal. So let's do the optimization. And at here, I will show you how to use the parameterized quantum circuit to make a kind of an optimization process and loop to get the best parameter for amplitude of our X gate per sequence. So at here, I define the parameter like an amp at here inside at the quantum circuit side. And there is my custom gate I declared, and it only have a 1 qubit. And I added it into our 1 qubit simple circuit and add a measurement. And after that, the circuit looks like this. And here I would like to test how can I insert some parameters inside of the first schedule. And this is how I did it. I declare some arbitrary value at here, and I built a kind of my schedule according to the predefined X pulses like this. So I wrote parameter comes from here and just simply change this value into a parameterized value of amp, like here. And after declare the pulse play schedule, I assign the parameter amp as as I predefined 0.18 adhere to the my schedule pulses. So after doing this, I can get this pulse schedule assigned the I values into here. So after that, we can add calibration of this schedule into our circuit. Oh, wait a minute. Where I lost. Okay. So the circuit have this parameterized schedule in here. So after running this, because this is a very arbitrary value, so it does not guarantee the best performance of Xgate. So it is just a kind of a temporal and trial and aim to show you how to use the parameterized value inside of a per schedule. Need some time. Okay, so it have a worse performance than our predefined Xgate, but now we will find the best value. So let's make a custom function to get a cost function like this, because I would like to return some, if there is a no zero population in our count dictionaries, I will return 0. So let's do some simple modification and simple optimization to get a best parameter, to get a best Xgate here. So it will take a little time. And as you remember, our predefined Xgate have an amplitude around 0.19, but the result may be a little bit different. And while we are waiting for the result, I would like to say that what is the fake backend? That the fake backend captures images like a performance and configuration of a real backend in some point. So if you can find some fake Washington and fake Mumbai, the performance and characteristic and values might be a little bit differ by our current real backend because it is not that updated that much frequently. Okay, we got the values and this fake Valencia backend to make a best Xgate for by using this fake Valencia gate, we need to use this amplitude to get the best performance. So let's use this value to make a best Xgate, and this is the flow. So yeah, I again make a parameterized quantum circuit, and after that I assigned our result value into this schedule and transpile it and make a schedule. And by using this schedule, I run the backend with 10,000 shots and drawing a count, and this is the result because this is the ideal result and this is our current Xgate result, but this is our calibrated one. So by I would like to show you how to use this custom pulse gate by using parameterized one to get a best performance to optimize the fidelity. And this is very important for you because even though we are not premium access users, you can use this pulse optimization and pulse control feature by using customized gate feature. So I'm just using a fake backend and simulator here, but you can try this code by using your public account to access to any 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 backend like Mumbai or any Pulse, yeah, IBM Q Pulse and Lima and other backend which not offer a open Pulse feature to open account. So I hope you tried this tutorial later. And my tutorial 2 is about gate calibration by using Qiskit Pulse gate. And at here, very simple calibration. I will calibrate the CX gate by using dynamic decoupling example. So with this tutorial tool, I will use pulse gate to get a better CX gate performance by using the technique named dynamic decoupling. And dynamic decoupling is used to increase the lifetime of quantum information. So if a qubit is idle, it becomes noisy because of the coherence, leaking information to surrounding. To prevent this idle state, we effectively disconnect the environment using so-called decoupling method. So scan the circuit for idle period of time and insert a DD sequence, dynamic decoupling sequence of gate in those spots. So this gate amount to the identity, so do not alter the logical action of the circuit, but have the effect of mitigating decoherence in those idle periods. However, this technique may not better the situation if we do not use a proper DD sequence because the pulse have finite lengths and do not implement perfect rotation. So as a result, it is very important to have an optimal decoupling sequence which does not destroy the qubit coherence instead of preserving it. So yeah, I need to change this because I first aim to use our best text schedule pulse, which we made above, but yeah, the usage is a little bit different. So I just using predefined XGate for show you how to use the DD by using the transpiler. So, and if we want to explore more explanation about the dynamic decoupling, you can take a look at the Nick Knows series of a dynamic decoupling site by clicking this link. So let's check our current gate performance. So at here, I will use 4 qubit and the simple x and cx to 0 and 1, and again cx to 1 and 3, third qubit, and measure and transpile and get the schedule, and the result is like this. Very long, and this is the place where dynamic decoupling works because dynamic decoupling's aim is preserve the first qubit, which have a very long delays according to its algorithms. And let's see how it works now. So before that, we would like to get the ideal result and our fake backend result. And there are a lot of error here. And at here, I will use the transpiler dynamic decoupling function, but Qiskit also have a Qiskit research libraries, and you can find how to use dynamic decoupling by using Qiskit research at our documentation. But here, let's focus on using transpiler pass messenger to use the dynamic decoupling. So maybe a little bit difficult because in in here, by using dynamic decoupling through the pass messenger, we need to check the period, means the duration of each gate by ourselves. So this is the command to check the duration. So the x gate duration is this, and cx between 0 and 1 is like this, and cx between 1 and 3 is like this. So I made a custom instruction duration arrays by using these values here. And after that, I declare the same circuit here and make a DD sequence by using FOR gate because X gate and X gate becomes an idle gate. So idle, so no changes in the logic. And after that, I use this pass messenger, schedule, duration, and dynamic decoupling method and make a DD edit circuit. And this is a timeline drawer of this circuit. And you can see that the X4 X gate is it's added after the CX operation of Q0 qubit. Let's check the performance. In these cases, the fake backend return more four results. No. No. Oh, yeah. our result returns a better result than just a fake backend result. So it means that it preserves information of a zeros qubit, and not allowing it to be coherent more. So this is how we use the dynamic decoupling, and dynamic decoupling means that we can use a pulse gate of a equivalent X gate to preserve information of a qubit by using these kind of functions. And our last tutorial this is a very new feature. And for doing this, you need to install Qiskit Research GitHub. And it is not that complicated. So I will share the link with you. And Qiskit community run a Qiskit Research Repo to support researchers. And yeah, so this function is newly added at there. And at here, we will do some error mitigation by using pulse scaling. So I'm keep saying that the CNAT gate is the problems, and we need to reduce, or we need to reduce the effect of CNAT gate of gate error. But in here, we can focus and reduce the amount of noise and its effect on our quantum circuit. So CNAT gates are a major source of error and generate the same amount of entanglement no matter what is needed in algorithms. So that is why we implement pulse scaling, which modifies the pulse used to create the CNAT to generate just the amount of entanglement needed, which likewise reduce the errors. And this method comes from this paper. So at this paper, the author tried to make this nice equivalent circuit. It is equivalent functional, but it reduced the effect, and it reduced and it limited the effect of entanglement just as we want. So by checking this circuit, we can see the effects, how it works, same. So let's make a RGG gate here between qubit 0 and qubit 1. And this RGG circuit, a gate is equivalent like this. There is a 2 CNAT gate and there is an ALGI gate between the 2 CNAT gate. And after using the scale CR pulse library by using this comment, no. You can see this decomposed circuit. So this is the decomposed and CR pulse scaled circuit that reduced the amount of entanglement which affect on our circuit, and it limited the effect of entanglement just as we want. So the below code is maybe very interesting. So at here, I made a very simple entangled circuit, which as you can see, the effect of entanglement gate will be very huge in here. So after just transpiling this, let's see the schedules, and oh, so messy, isn't it? And so there are 4 entanglement plus resonance gate here. So very messy, and they have a long duration of a whole circuit here. Let's start. Let's check the ideal result and the fake backend results here. So this is the ideal result by running a state vector simulator of air. And this is the fake backend result by using our fake Valencia. So the result is pretty different. And at here, we start implementing the add dynamical decoupling function from Qiskit research.utils and convenient libraries. And we can call QC our quantum circuit and declare some backend and control set the option like unroll RGX to PCR true, and the result circuit is like this. And let's transfer the circuit and check the schedules first. Okay. Our previous circuit duration is 33,200 steps. And here, there is a small reduction here, like this. The, the number of a entanglement gate is same, but the aim of this per scaling is reduce the amount and effect of an entanglement gate. So let's check the result. So at here, you can see several plots and state population is closer to the ideal case than fake backend. So this is how the per scale works. So yeah, this is the end of my tutorials, and I'm happy to receive some questions from you. Thank you. Okay. I can see no questions to the chat. And is there any questions? Hi, Manjula. This is the end of my talks, and please kindly let me know what is the next process, and I'm waiting for the question from our audience. Thank you for listening.
Ma'am,
Yep.
participants, please free to ask questions. Any questions if you have. Ping
Yep.
on
Yep.
chat box. Okay, I think there is no questions.
Yeah, I quit it earlier than you
Uh,
planned.
Ma'am, thank you for your comprehensive session on Qiskit Pulse tutorials. It was very informative.
Yes. And
And I
the
think,
yes, tutorial 2 and tutorial 3 is a very new feature of Qiskit Pulse side and Qiskit research side. So this is a very new tutorial for everybody. So please try this. And I want to say that there are some limitation to an open account, means a public account users that you doing this kernel developing side by using Qiskit Pulse or Qiskit Experiment or Qiskit Dynamic side. But I want to say that the tutorial 1 showed how to show the way how to use the Qiskit Pulse optimization by using your just own public account. So please try that functions to your backend by using your public account if you want to
okay.
do. Yeah.
And the whole session is recorded, so participants, if you want, you can check out it in Discord channel. So, and also, please fill the feedback form. And we arrived to the end of our session, ma'am. I once again thank you for joining hands with us to make the session wonderful success. So I would also like to thank Dr. Manjula Gandhi, ma'am, for leading and supporting us throughout the process. And I thank everyone for joining the session. Thank you.
Yeah. Thank you very much.